Okay, the next is a important relationship between the PDF and CDF for a continuous variable. So we have a variable x which has a PDF of f of x, and let's say this is the distribution and this is 0 and this is a is equal to 0 and this is b which is equal to 1. So this will be the distribution, this is and this is the whole thing is equal to 1, and x so f of x is 1 if x is more than or equal to 0 and it is less than 1 and it is 0 otherwise. So f of x is 1 as long as the value of x lies somewhere here. Okay, this is basically a uniform PDF for the interval 0 and 1 because it is between 0 and 1. The uniform PDF is x is equal to 1 minus b minus a, but since b is 1, so it's going to be 1, and a is 0, so it's going to be 1. So that is why f of x for a uniform distribution in the interval of 0 and 1 is going to be f of x is going to be 1 when a is equal to 0 and b is equal to 1. So what is going to be f of t is going to be negative infinity to t f of x dx. So it's interesting to see this in a graphical format. Say example, this here we are representing f of t, and this is 0 and this is 1. So obviously as we go from 0 to 1, the f of t is going to increase, and at 1 it's going to be maximum, it's going to be 1 because it's 1, and then after that it's just going to stay. So what here is the differential. So if this is f or t, what is going to be the over here, the dx over dy is going to be 1 because it's a straight line here. So it's going to be 1, which is basically f of t over dt, and 1 is also f of x, f of t. So you can see for so f of t, this is this number, and dt, which is this, is going to be 1 because this is rise and run are the same, and we've already seen that f of x is 1. So which means that f of or f df, which is what this is, df over dt is equal to f of t. So this if s lies between 0 and 1. So for most places we can get the f of t just by differentiating ft with dt. What happens when it's here? When it's here, there is no rise, so it's going to be 0 anyways, and here also it's going to be 0, although the f of t is 1, but if you try to differentiate it here, this is going to be df over dt, but df is 0, so this is going to be 0, and same as here, df is going to be 0. So we can get the density function at most places where it is interesting because it's changing, or distribution function is interesting by differentiating it. So that's one, and now let's do an example of it. So example, x is a uniform on 0 and 1, and now let's say that we have another variable that is y, and that is represented by y is equal to x square. Now we know that f of t, this is a derived random variable. This is a derived random variable. Okay, so we are so f of t is going to be probability of x less than or equal to t, and since this is 0 and 1, so we have again the same situation here. It is 0 and 1, and if you have a t here, if you have a t here, it lies between 0 and 1, then f of t is going to be t. And why f of t is going to be t? Because for a uniform distribution which is 0 and 1, the f of x is going to be 1. Again, why f of x is 1? Because it is height times length is equal to 1, and the length, height is the f of x, and the length is 1, so this is going to be 1 by 1, so that is going to be 1. So in this situation where t lies between 0 and 1, the f of x is 1, so it is 1, so the whole area of this thing is going to be 1 times t minus 0, which is t, so this is going to be t. So that is why f of t is equal to t. And obviously if it is less than 0, then f of t is going to be 0, and if it is more than 1, then f of t is going to be 1. Now, so we know this now, that f of t is equal to t. Now let's assume that for y the distribution function is given by g of t. So g of t is going to be probability of y less than or equal to t, but y is x square, so that is given by x square is less than or equal to t, which is going to be probability of x is less than or equal to under root t. So g of t is going to be under root t because of the same thing, because it's 0 and 1. So we have seen that f of t is going to t based on this. G of t is going to be under root t as long as t is more than or equal to 0 and less than or equal to 1. So then g of t is also going to be 0 if t is less than 0 and 1 if it is more than 0. So now we know that df over dt gives you f of t. So it will also be g of y is going to be dg upon dt, and we know the g now, so it's going to be g of y is going to be d under root t upon dt. This we can then differentiate. If we differentiate this d under root t over dt, you're gonna get g of y is equal to 1 upon 2 under root t. So this is how we can calculate the g of y, or the PDF of a derived variable, by differentiating. Once we get the g, we can differentiate it, we can get to this simplified formula, because once we get to g of t, all you have to do is replace this g here or here, and then you differentiate it. So that's the derived random variable application. Next we're gonna do in a similar pattern, we're gonna do another question which is the same. We start with a uniform random variable. We start with a start from here. We start with a uniform random variable. So we'll start with a uniform random variable, and let's say that x is a uniform random variable between 0 and 1. Again, it's a uniform random variable 0 and 1, and if it's a uniform random variable between 0 and 1, then the f is going to be 1. Fx is going to be 1. So f, and if there is a variable here which is t, f of t is going to be t for t which is more than 0 and less than 1. Now, so that's all okay, but now we have a variable y which is a negative log of x. So if y is a negative log of x, then what happens is that if x is 0, then y is going to be infinity, and when x is going to be 1, then y is going to be 0. So y will lie between 0 and infinity. So the thing with log is that when you have a log to the base 5 of 0.5, it's going to be minus 0.69. So but when you put negative log of 0.5, it's going to become plus. So that's why it's make it easy for us to calculate. So that's why we're going to be y is negative log of x. So what we want to do here is we want to calculate the distribution function, which is the CDF of y, and from there we need to get the PDF of y. Okay, so let's see, g of, let's say it's g is the function, is the PDF or CDF. So g of t is going to be probability of y less than or equal to t. So we're gonna say py, I'm gonna put a x variable here, log e x is less than or equal to t, which will become probability of log x negative, we remove the negative sign here, probability of log more than or equal to t, which is another mathematical rule here, that this will become probability that x is more than or equal to e to the power minus t. So log x is more than or equal to t, log of base e, then x can also be written as more than or equal to e to the power t. So that comes from a logarithmic laws. Now what exactly is a uniform? If there is a uniform distribution, then we know that probability of x less than or equal to s is going to be s, and probability of x more than or equal to s is just going to be 1 by x. So probability of x more than or equal to e to the power minus t is just going to be 1 minus e to the power minus t. So that is g of t. Now we know that dg over dt is equal to g of y, g of y. So what is g will come here as d of 1 minus e to the power minus t divided by dt, and then when you solve it or differentiate it, you get e to the power minus y. And what exactly? So we're getting a g of y is equal to e to the power minus y. Now what is g to the gy? So if you look at if you remember the exponential PDF of exponential distribution with the parameter of lambda is going to be 1 by lambda e to the power minus e minus x upon lambda. So if lambda is equal to 1, then it's just going to be e to the power minus x. So here it is y. So this is just a distribution of the exponential distribution. So we are starting with a uniform random variable. We taking a log of it. Now what you get is another random variable, but it has a exponential distribution with lambda of 1. So a uniform random variable, logarithmic, it becomes an exponential distribution with a lambda of 1.